Today we're going to talk about the law of sines. And the law of sines is one of the cases where I'm actually going to, generally speaking, encourage you guys to use a calculator, because it honestly, a lot of these problems that you're going to be doing, you're going to want to use a calculator to get approximations. Now, before we talk about what is the law of sines and why is it interesting and important? Well, the thing is that up to this point, when we've talked about trig functions, we can really think about them coming about in two different ways. The first way that we think about them, or one of the two ways that we think about them at least, is we think about them from the unit circle, right? So we take our unit circle, we have some angle around the circle theta, then we look at the terminal point, and the coordinates of the terminal point are cosine theta and sine theta. That's just by definition how the trig functions are defined. Now, the thing is that we can think about within this unit circle, there is then this right triangle. And so a second way of thinking about this is that if I have a right triangle and some angle theta, here's the hypotenuse, here's the opposite side, and here is the adjacent side, then we can say that the cosine of theta is equal to the adjacent side divided by the hypotenuse, and the sine of theta is the opposite side divided by the hypotenuse. So the trig functions, on the one hand, they're defined in terms of the unit circle, but on the other hand, they really are about right triangles. They tell us something very fundamental, let's say, about how right triangles are shaped. There is, of course, a problem. Most triangles in the world are not right triangles. Now, surprising numbers of them are, okay? Like, there's a lot of them that are actually right triangles that you might encounter in the real world. Why? Well, because humans like to build things that are perpendicular. And even in nature, you get a lot of things that are perpendicular. So, for example, trees tend to grow straight up out of the ground. So if you had a problem that involved, we have some tree here. I can only draw pine trees, so that's what you're getting is a pine tree. It's actually kind of a dead pine tree from what I can tell. But you have some tree. Well, often you can kind of think of the tree as being the height in some right triangle if you have to deal with a triangle. If you're dealing with a problem in architecture or something, again, most people like to build walls that go straight up. So you end up with a lot of perpendiculars involved. Right triangles are actually pretty common. However, not all things are right triangles. Not all triangles are right triangles. Obviously, not all things are triangles, but not all triangles are right triangles. And so what if we wanted to talk about the dimensions of some kind of a triangle that is not necessarily a right triangle? So I just have some arbitrary triangle here. Let me draw it in a way that makes it very clear that this is not a right triangle, hopefully. And I have these three different angles in it. And I'm going to label these angles as A, B, and C with little lowercase letters. And then we're going to have capital A, capital B, and capital C. I'll put a little underline under this to emphasize that this is the capital C, because otherwise you're going to have trouble with my handwriting knowing whether I'm saying capital C or lowercase c. Now notice that in this setup, capital A is the side which is opposite to angle little a. Capital B is opposite to little b, and capital C is opposite to little c. The question is, what can we say about the dimensions of this triangle? Well, it turns out that the law of sines tells us a great deal of information about this. And it might be a little bit surprising that you get this kind of a result, but you do. So what the law of sines says is that the sine of the angle little a divided by the length of the side A is equal to the sine of little b divided by the length of the side b, which is equal to the sine of little c divided by capital C. Of course, we could take the reciprocals here as well. You could say capital A over sine of little a is equal to capital B over sine little b equals capital C divided by sine little c if you wanted to, these are both valid ways of doing this as long as none of these are 0, which if this is really a triangle, then none of the lengths or angles can be 0. If any of them were 0, then that would mean it's not really a triangle. It's like a triangle that's collapsed down into a one-dimensional line. So it actually turns out that even though the trig functions are sort of naturally suited to talking about right triangles, they actually tell us something about arbitrary triangles. Now, when can you use the law of sines? When could you use it to say something about the dimensions of a triangle? Well, the answer to that is you can use this to say something about the dimensions of a triangle whenever you know a side and an opposite angle. So you need to know one side and you need to know an opposite angle. It turns out you actually need to know a little bit more than that. You need to know one more side or angle. So you actually need to know 3 measurements of your triangle in order to use the law of sines. But 2 of those measurements have to be one of the sides and the angle which is opposite to it. So if you think about a triangle, let's redraw that triangle. There are 3 angles here to think about, and then there are 3 sides. And so there's really 6 measurements about the triangle. Well, the point is, you need to know 3 of them in order to be able to figure out the other 3. So in order to know that we have a side and an opposite angle, there are 3 types of measurements that we could have. We could have what is called the side angle angle case, which is abbreviated as side angle angle. That means that I know one side and I know both angles on either side of it. Or we could have what is known as the, I should also mention, it's not just written as side angle angle. It is also sometimes called the angle side angle. And we'll talk about why all of these names are the way they are in just a moment here. The other possibility is that you know 2 sides and the angle opposite one of them, in which case it's called side-side angle. Both of these triplets of measurements, you can solve the triangle, you can find the other measurements by using the law of sines. Now, how does that work? Well, let's suppose that I give you a triangle and let's start with the sort of with the side angle angle or the angle side angle case. Let's suppose that I were to give you a triangle and I were to say, okay, so here's your triangle. Let's say that this is an angle of 20 degrees and let's suppose that this is an angle of 60 degrees. And what you know is that this side is a length of 4. And I want to solve this triangle. So let's say that this side down here is going to be side B, and this side up here is going to be side A, just as for the sake of example. Well, the way that we can deal with this is, first of all, notice that what is given to me is a side, the angle next to it, and then another angle. So this is side angle angle in terms of the measurements that are given to me. The key point here is that I know this measurement of this angle and the side opposite to this angle. So I know that 4 over the sine of 20 degrees is going to equal A over the sine of 60 degrees. And that means that the side A is going to equal 4 over the sine of 20 degrees times the sine of 60 degrees. Now, in this case, I happen to know what this is equal to. So this is equal to 4 over the sine of 20 degrees times square root 3 over 2. So this comes out to be square root 3 over the sine of 20 degrees. But the truth is, a lot of these you're just going to have like random angles that you don't really know. So you should really just plug them into a calculator when you're doing these types of problems, okay? Don't like think, oh, I need to find exact values for all these things or anything like that. This is one of those rare times when I'm going to tell you you can use a calculator pretty much every time. Or if you wanted an exact value, you could leave it in this form. Just leave it in terms of sines, okay? That would be fine too. Now, this tells me the length of side A. But what about side B? Well, the problem is that I don't know what this angle up here happens to be. I don't know what little b is. It's not given to me. But I do know what little b is. And that is an important factor. I know what is little b because I know that these angles have to add to 180 degrees. So b plus 20 plus 60 is equal to 180. That means b must be equal to 100. Okay. So what does that mean for me here? Well, that means that I can now do the same trick as I just did. And I can say 4 over the sine of 20 degrees is equal to b over the sine of 100 degrees. That means that b is equal to 4 over the sine of 20 degrees times the sine of 100 degrees. One thing to be really careful about when you plug this stuff into your calculator, make very sure that you are working in degrees or radians as appropriate. One of the easiest mistakes to make when you do things with a calculator is to accidentally enter things wrong. You're trying to enter the right thing, but you end up entering something that is not quite right because maybe your calculator isn't configured correctly. Okay, so enough about that. Just be careful when you plug it in. Make sure you're using degrees or radians, whatever you have in the problem. So notice that as long as I know 2 angles in the triangle, I always know the third angle. So if you know 2 angles, you can always find the third angle, which means you can always use the law of sines as long as you know one of the edges. So what we can say, really, is that 2 angles plus any side means I can use the law of sines. Essentially, because 2 angles really means we know 3 angles, since we know that all of the angles have to add to 180 degrees. So it doesn't matter which 2 angles you are given in the problem, you know the third angle as well, just from this fact that all angles add to 180 degrees, or pi radians if we happen to be working in radians. So this takes care of what are called the angle side angle cases, or the side angle angle cases. Those are kind of the different configurations. But instead of just trying to remember these like angle side angle or side angle angle, I just think about this as 2 angles plus any side, okay? That's what you're really looking for in order to use the law of sines here. There is a second case where you can use the law of sines, but it is a little bit more complicated to think about. The second case where you can use the law of sines is if you know 2 sides plus 1 opposite angle. Then you can use the law of sines as well. So let us take a look at an example where I know 2 sides and I also know one of the opposite angles. So let me draw a triangle here and let's see if I can actually draw this thing reasonably. So let's say I know that this side has a length of 4 and let's say that this side has a length of 6. And let's suppose that what I know is that this angle is 25 degrees. So I think this should work out nicely. Then what I can do is I can say, okay, well, let's call this angle little a and this angle little b, and we'll call this side b. And then what I know is that 6 over the sine of 25 degrees is equal to 4 over the sine of little a. This means that the sine of little a is going to be equal to 4 times the sine of 25 degrees divided by 6. And this is going to equal 2/3 times the sine of 25 degrees. So now I just need to figure out what would be the angles that would work with this triangle and would also have a sine that is equal to 25 degrees. Now, I don't offhand know what is the sine of 25 degrees, but we can figure that out easily enough, and then that is going to give us our answer here. Now, what I want to note here is that once I know what is the angle A, well, then the rest of this follows like in the previous problem, because once I figured out what is A, okay, then I know all 3 angles, because I can figure out what is B, and then I can just say that B over the sine of B is equal to 6 over the sine of 25 degrees. And I can solve for B once we know little b, the angle. Okay, so once I have figured out what is little a, the angle, I can figure out what is little b, the angle. I will let you guys plug that in since I don't actually have a calculator here with me, and I will leave it to you guys to deal with that. Now, there is a complication that happens when you are dealing with these types of triangles, and I want to show you what that is. The problem is that you can end up with impossible triangles, and you can end up with triangles that have got multiple solutions. So I want to illustrate why that would be the case. Let's suppose that I give you this angle down here, and let's say that I say this is, 45 degrees, because I want to make this into something that is reasonably straightforward to work out. Let's suppose that that is 45 degrees, and let's say that this is a side of length 2. And I tell you that this side up here is a length of, let's say, 1. Well, the problem that you're going to find here is that this is not possible, okay? So I've given you 2 sides and an angle. Now, the problem is that when you do this, what you would find is that whatever triangle you had here, whatever this angle would be, let's call this little b, you would find that the sine of b over 2 is going to have to equal the sine of 45 degrees over 1. Well, that tells you that the sine of b is going to have to equal 2 times the sine of 45 degrees. But what is the sine of 45 degrees? Well, the sine of 45 degrees is actually the square root of 2 over 2. So this comes out to be 2 times square root 2 over 2. The 2's cancel, and I get the square root of 2. So the sine of b is the square root of 2. We're all set, right? Does anybody see a problem with this? Give you a minute to think about what the problem could be. The problem is that there are no angles whose sine is the square root of 2. Square root of 2 is not in the range of sine. That means this is impossible. This is an impossible triangle. So, if you ever saw somebody give you these kinds of measurements in the real world, you know somebody somewhere has made a mistake with their measurements, because this is not physically possible. It's not simply not physically possible, like it's not just against the laws of physics. It is fundamentally against the possibilities of geometry, at least in a Euclidean universe, a universe that obeys the usual laws of Euclidean geometry. So this is an impossible triangle. There are other ways in which you could end up with an impossible triangle as well. So let's think about here what happens when you have side-side angle. There's 3 possibilities, although kind of 4 possibilities, depending upon how you want to think about it. What are the possibilities? So let's say that these are the angles that I give you. I give you this angle here, and I give you this side, and I give you this side, capital B. Okay, one possibility is that B is too short. So you'll notice that no matter what I do here, I could never build a triangle like this because this line segment can never reach this line down here. So that means that this is an impossible triangle. Another possibility is that B is too long. So I could, instead of having it be too short, maybe it's so long. Well, actually, no, that's fine. Sorry, so yeah, that's not impossible. This is just the next case that we want to look at. So the next possibility is that same kind of setup, my length for B might be very long. In that case, if you think about swinging around this B, what you find is that there is only one triangle here that makes it work. Okay, so this is another possibility. You might get one where there's only one option here. Now, when you do this, you might find, well, but it actually, you could also form this triangle. Yeah, but that would be a different triangle than what we originally had. So that is a case that where there's really only one triangle that obeys our original constraints here. A third possibility is that there are 2 choices. So maybe the dimensions come out in the following way. I give you this angle and I give you this side A, and then I give you a side of length B, but maybe there's actually 2 different triangles that will match this up. There's this triangle over here that I've shaded in, and then there's this bigger triangle here that I've got. So there's actually 2 different possibilities. So in this case, there's an ambiguity. There are actually 2 possible triangles that both have the same side-side angle measurement in this case. How would you know that this happens? Well, what you would find is that there's going to be 2 different angles whose sine is the correct sine, and such that together with the first angle, they sum to something under 180 degrees. So we need 2 angles with the correct sine and when I add this angle up here, so let's call this angle little b and this angle little c, b plus c needs to be less than 180 degrees. We also need that c has to be bigger than 0. One final possibility, which is sort of a fourth possibility, but not entirely. It sort of behaves like what we just saw, but it's actually just a single solution. The final possibility is that you actually end up with a right triangle. So it's possible that I give you some angle and some side here, and then I give you some side of length b, such that there is only one solution because b is just long enough to get from this point down to this line segment at exactly 1 point. So this is one solution where this angle, little a, has to be equal to 1. In that case, we just get a single solution instead. Now, I want to make sure you guys see examples of all these things, so please take a look in your book at examples 3, 4, and 5 on pages 684 and 685. Those illustrate the 3 cases that we just saw. I would write them down on the board, but I don't think it's any more helpful to see it written down here than to just see what they said in the book. The book does a really good job explaining these cases. I would also refer you guys to the whatchamacallit, the My Math Lab videos to see more examples of this stuff. Okay, so just keep in mind that in side-side angle, there is some ambiguity. You could get 0 solutions, 1 solution, or possibly even 2 solutions. Now, you might wonder, what about the other possibilities? What if instead of having one of the types of measurements we were thinking about today, what if you had some other combination of measurements? Well, it turns out you can actually deal with those as well. You deal with those using something called the law of cosines. And that is what we will be talking about next time.